Okay, guys, got another example for you. Rapid HIV testing. Again, finding the probability of at least one, just like we did with the couple looking to have at least one girl in their family. Many people who visit clinics to be tested for HIV, the virus that causes AIDS, don't actually come back to learn their test results. Clinics now use rapid HIV tests to give a result while the clinic waits. A rapid HIV test. Well, we've heard of some rapid tests recently in our history. In a clinic in Malawi, for example, the use of rapid tests increased the percentage of clients who learned their test results from 69% to over 99%. Okay, this ought to sound familiar to you. The trade off for fast results is that rapid tests are less accurate than slower laboratory tests. Applied to people who have no HIV antibodies, one rapid test has a probability of about 0.004, less than 1%, of producing a false positive, of falsely indicating that antibodies are present, saying somebody that's sick when they're not, basically. If a clinic tests 200 randomly selected people who are free from HIV antibodies, what's the probability that at least one false positive will occur? They test 200 people. I don't know if they would do that in a day or like a month. I don't really know how any of that works. But let's say it's a month. If they test 200 randomly selected people who are free, what's the probability that at least one person will, according to this test, be told that they're carrying the HIV virus? Assume that test results for different individuals are independent. Now, I don't really have a spot for writing this, but I want to do it anyway. The probability of at least one false positive. Well, that's going to be equal to 1 minus the probability of none. No false positives. So they say that the probability of a false positive is 0.004. So the probability that they get it right is 0.996. So wouldn't this be 1 minus 0.996 for them correctly coming up with a negative, times another 0.996 for them getting the second person correctly negative, and so on until we have 200 correct negatives. So it would be 1 minus 0.996 to the 200th power. Put that in the calculator, and you actually get, are you ready for this? 0.5514. There's a 55% chance that when you use this rapid test with 200 people, that you'll get at least one false positive. I mean, it's kind of hard to process, really. 0.004 was the probability that any one of them gives a false positive. But if you take that tiny little probability and you do something 200 times, it makes sense that at least one of them might come up. And so here's how you find that probability. The probability of at least one is 1 minus the probability of none. This is the probability that we don't get a false positive, that it actually works correctly, and then we get a correct negative. We would need 200 of those for there to be no false positives. So 1 minus 0.996 to the 200 gives us a 55% chance that if you test 200 people with this rapid test, you might come up with a false positive and pretty much wreck somebody's day right there. Okay, at this point, it's always good to take a minute and review our probability formulas. So here we go. The probability of A or B, this is from a couple of days ago. It's the probability of A plus the probability of B minus the probability of A and B. Think of the Venn diagram. If I add up one circle and the other circle, I have added the overlap or intersection twice, so I've got to subtract it once. Now, I do have a formula for the probability of A or B that goes just the probability of A plus the probability of B. We've actually used that once today, but that has to be if they are disjoint, meaning they cannot happen at the same time. There's another phrase for that. It's called mutually exclusive. All right. We have a formula for A and B. So I want to put a little bracket around here and point out that these are the OR question. I'm going to put a little bracket around here and point out that these are formulas for the AND kind of probability questions. The probability of A and B, the general multiplication rule, is that it's equal to the probability of A times the probability of B given that A actually happened, or that we know A is going to happen. Now, I have another formula that we have used today where I can multiply just probability of A times the probability of B or a whole 200 of them together if A and B are known to be independent. And in both the rocket problem example and the rapid HIV test problem, they told us that tests and O-rings work independently, so we were allowed to just multiply them together. Okay, then we did have one more. It came from this one. It was algebra from this one. The probability of A given B. That's not A given B, so I've rewritten this a little bit, but it goes like this. The probability of A and B in the numerator, and the probability of the condition in the denominator. So probability of B in this case. And then here we have one more. So the probability of at least one, we've seen it twice today already, is 1 minus the probability of none. Did that with the probability of getting at least one girl out of 4 kids, 1 minus the probability of all 4 boys. And then we just did it here with the rapid test. The probability of at least one false positive is 1 minus the probability of no false positives. And that probability ended up being something to the 200th power. All right, next page.